Hey, what's up, everyone? Joe here from Fluid Numerics. Today we're going to be talking about continuous integration for Fortran applications using Google's Cloudbuild. So let's just go ahead and dive right in. So first off, let's talk a little bit about what continuous integration is. In general, continuous integration it's a development practice where developers integrate code into a shared repository frequently, usually multiple times per day. So you might have, a team of developers who are kind of working independently on different tasks, and they're contributing code to a shared repository between them. And the idea behind the other half of the continuous integration process is that every time a push is made to a shared repository, we want to be able to make sure that the application builds, it runs, and it gets the right answer every time. So the idea being here is, if let's say this developer up top here pushes a commit to the repository, we should have some mechanism to trigger a series of events to actually happen over here. So on the right hand side, what we might have is, in the case of Fortran applications, usually the first thing we want to do, of course, is turn that source code into a binary or a set of libraries. And so we execute a build. And then once that application is actually created, of course, you might want to just run it and make sure that it runs without hitting segmentation faults or some serious errors. Now, in most cases, just running the application is not enough. Specifically when you're getting into some of the domain sciences, you actually want to make sure it gets the right answer. So we'll say we'll have a test phase here where you might be running through a series of unit tests or integration tests. And then, of course, if all these things pass, if you're able to actually create an application, if it's able to run without failure under the conditions that your end users actually want to run it underneath, and of course, if it produces the correct results, you usually want to publish some type of artifact. Now, what that artifact might be, it could be a Docker container image, it could be a Singularity image, it might even just be a package of the application binary and maybe some of the shared object library files. But the idea being is, no matter who pushes to that repository, you want to be able to run that same set of tests every single time to make sure the application is running without failure. So let's talk a little bit more about each one of these steps here, and we'll just start off just by talking about the build process. So what should a build pipeline do? So we kind of covered it just very generally here. A build pipeline really needs to answer the following questions for us. We need to know, does the application build? So does it build? Does the application run? And does it get the right answer? Okay. Now, when you're thinking about compiled applications and when you're thinking about scientific applications in high-performance computing, generally, this question's getting really complicated these days because there's just a lot of hardware out there. And so what we really want to be doing this day and age is answering this question: does it build? Does it run? Does it get the right answer on a variety of platforms? And the few that come to mind for me are: does your application successfully do all three of these things on serial CPU with serial CPU builds? So you might be running just on like x86 platforms with one core. Of course, you might have something where you're running with OpenMP or MPI or MPI plus OpenMP, and so you'll have parallel CPU only. And then you might, of course, with GPU accelerators becoming more and more commonplace in scientific computing, you have a couple scenarios that can arise here. You might have an application that runs just on one GPU, or you might have your application, especially if you're getting ready for some of the exascale computing platforms, you have your application ready to run on multi-GPU platforms. Now, to make this story even more complicated, over the last couple of years, there's been more and more push of diversity in the GPU hardware space. So we don't just have NVIDIA GPUs anymore that are with applications written in CUDA and OpenACC. We now have new things like ROCm and HIP coming out, and of course Intel's One API. And so now we have to make this sort of portability problem a little bit more complex on the GPU side. This might also include, you might have customers who have a variety of GPU hardware. So this could be AMD, NVIDIA, or Intel GPUs. And of course, your build pipeline ideally is going to address some or all of these particular cases, but you're answering those same three questions underneath the hood. So there's a lot that would need to be done. And of course, if you were doing this manually every time you want to commit something to your repository, it certainly would slow down your development process. And it's best really to try to automate that as much as you possibly can. So let's talk about each one of these questions in turn, and then what we're going to do from there is just get into a very quick example to show you how to set up a very simple build pipeline that will answer the questions of does it build, does it run, and does it get the right answer on a serial CPU-only platform. Next week, we'll be looking at doing all those same things, but on a single GPU platform. All right, so what does it mean when we're what do we need to do to answer the question, does it build, when we're creating a CI pipeline? So let's talk about what I'm going to call the ingredients for building. Okay, so with Fortran applications, and I guess this really could apply for any compiled application, or it might even work for Python applications as well. What we need first is a consistent build environment. So this is our starting point that we want to use to always run through the compilation process to create our application. And this includes like a specification of an operating system and maybe a minimum set of dependencies that are available before you actually start building your application. Now, some examples of tools that help you have a consistent build environment. Of course, containers are a popular platform for doing this, and this would include services like Docker or Singularity or anything like that. And essentially what container platforms provide for you is an isolated, reproducible environment from which you can start from. Now, if your application isn't already, isn't what we would call container ready, or if you just haven't written a Docker file or a Singularity file, you might think about, okay, well, maybe you would want to get yourself into a state where you could use that. But of course, there are other strategies. You can use virtual machine image platforms that allow you to basically bypass the need for using a container, but of course you end up with a different artifact here. But under the VM images, you have services like Vagrant, which again, the whole idea with some of these is really you're specifying a starting operating system and perhaps some already available dependencies for your application. Outside of Vagrant, another popular one is Packer. Both of those are provided from HashiCorp. All right, so once you have a build environment, so you always are guaranteeing that you're starting from the same point with every build that you do, you need some kind of make system. Now with Fortran applications, and again this also applies for C and C++, you have a few common options that are out there. Of course, you have the classic make file, right? You have CMake, a CMake build system, and the difference between CMake and a make file is a CMake system really will do some auto detection of the platform you're trying to build on, maybe some of the dependencies that are already there, and it will create the make file for you from which you can then use to actually build your application. Same thing goes for AutoConf. AutoConf is very similar to CMake in that it's sort of like this meta make system. You can make a make file with it, which again, the make file is really just providing those instructions on how to turn each one of your pieces of source code into an object file or a binary. And those of you who work with like legacy Fortran codes, I'm sure this last option here is not foreign to you, but a set of bespoke shell scripts to go through that compilation process. I've seen my fair share of those since I've been working in Fortran. All right, but in any case, you have a consistent build environment. If you have a make system, so the make system being the recipe to turn your source code into a binary or a library, most applications come at least with that make system. And more so nowadays, people are starting to have things included in their repositories like a Docker file or a Singularity image file, or some type of Vagrant environment to start from. The last thing we need to have here, and this is the key ingredient that specifies the list of steps or the list of commands that need to be done inside of that build environment to create your application. And so I'll just call this build instructions, and this really is and it's kind of overlaps with the build pipeline, but it's really, so for example, if you have a Docker file in your repository, the build instructions there would be to call docker build on that Docker file to create a Docker image. That's really it. So those are the three ingredients we need to have there. Now, in terms of the services that are available for doing this, there's quite a few out there. Over the last couple of years, I've seen a lot of folks using Jenkins, and you can have Jenkins pipelines that basically they're connected to your Git repository, and whenever certain events happen in your Git repository, like a push to the repo on a particular branch or a push of a specific tag, it goes through and actually creates the Docker images and publishes them for you if everything passes. So Jenkins is the popular one. Of course, Bitbucket. Most of the Git repository providers out there have some type of CI pipeline or build instructions set up integrated. So you have Bitbucket. These are the CI pipelines. You may have heard of GitLab runners, and all of these essentially provide you an interface to specify your build instructions as a YAML or a JSON file that you could just stick in your repository. And of course, today we're going to be talking about how to use Google's Cloudbuild, which is another option. All right, so again, those basic ingredients are a consistent build environment, a make system, and then some set of instructions that are set up inside your repository that can be executed whenever a push to your repository happens. So let's talk about the next step here. This is kind of an important one, but one that's not really handled by the CI infrastructure. Your application has to come with a set of tests to be able to make sure your application runs and gets the right answer. So I just wanted to give you, in case you're not familiar, a description of the two types of tests that are commonly used for testing scientific applications or most software applications that are well supported. So we have on one side of the test here, we have what are called unit tests, and we have integration tests. Now, integration tests is what I've commonly seen used in Fortran applications, and the reason why is, like, a lot of scientists, what they'll do is they'll write a Fortran app. Might be for weather modeling or space weather or molecular dynamics, or they're doing some type of fluid flow, and what their ultimate goal is to model a physical scenario, and then they'll go through this process of tuning that model to get a particular answer, and they'll publish a paper on it. And at that point, they've got an implementation of the model, which when thinking about that in relation to the code, you're really combining a whole bunch of subroutines together in some organized fashion to take an input and produce a validated output. All right. So an integration test takes a known input and it returns a validated output that's trusted, and usually this is called a gold standard. And if you want to modify your code down the line, so long as you're not changing some of the underlying physics or the chemistry or whatever it is you're doing, like if you're just porting to a new platform, of course you want to make sure you're getting the right answer. What folks will do is they'll run a series of validated examples that exercise various routines in their application and compare against this gold standard or validated output. This is very common set a test to include when you're asking the question, does it run, does it get the right answer? Usually those tests are relevant to the end use cases that you or your customers are interested in. Now, unit tests, they're written with a little bit of a different mindset. A unit test is meant to really exercise a very small portion, usually just a single subroutine of your source code. And the way that's done is, if you have a subroutine that has, 3 different inputs, what you would do is you would call that subroutine varying those 3 different inputs over a range of valid values, and you would have some way of evaluating whether or not that subroutine behaved properly and or gave the correct output. So it's usually testing individual subroutines, with known and varied input. The output is compared against verifiable results. So that's really kind of the 2 different strategies you can go with. So if you do have an application that doesn't have unit tests, but you have integration tests, or you have some validated examples to start with, that's really all you need to help yourself get going. Now, I do encourage you to have a mix of both of these with your application. Of course, everyone's always working towards that idea of making sure we're testing every possible scenario for our application. Okay, so that really covers what I wanted to talk about in terms of continuous integration. We have this idea that what we want to do is compile our code inside of a container or some type of fixed starting point environment. We want to run the application there, and then we want to make sure it's getting the right answers. And if all that happens, we want to publish some type of artifact, and we want that to happen automatically every time. So today's example, we're going to be looking at a code called the spectral element libraries in Fortran. You can find that at github.com/fluidnumerics/self. If you go on that repository, you'll see this will give you some type of examples on how we're setting this up with Cloudbuild. You're kind of seeing this journey unfold as we go through it ourselves. So keep in mind, it's all a work in progress, but we do hope you find it valuable. And let's talk a little bit about this application before we actually look in the source code here. So this is a mixed Fortran plus C++ application, and the C++ portion is only there because we're actually using AMD's HIP to do GPU offloading. So it is a GPU accelerated app that's meant to run across AMD and NVIDIA hardware. Okay, and we're still in the works of putting the multi-GPU stuff in there. But where we're going to start today is just focusing on getting this application to build with HIP, and of course setting up the build triggers to have that automated testing happen. Okay, our make system, it's just a make file that we have right now. We're still working on our CMake system, but in terms of some of those build ingredients, we have a make file. For our build environment, we're using Docker. Okay, and again for that build pipeline, we're going to use Google Cloudbuild. So with that in mind, let's go ahead and jump over to the Cloud Console. Now, if you did want to follow along, if you do have your application that you're working on as well, just head on over to console.cloud.google.com. If you don't have an account, go ahead and get it set up. And we're going to be doing 2 things here. First, once you get to the main console page, it should look something like what I'm showing you here. But up on the top right, there's an Activate Cloud Shell button. This will give you a Linux or a terminal environment in your browser. It has Git and a lot of other tools already pre-built and configured for you. And you can do a lot of your development here. And of course, using Cloudbuild, you can use some of the resources on Google Cloud to do all your testing. All right, so once that comes up, you'll want to go ahead and set your project. You can run Gcloud Config set project, and for me, this is self fluids. Ultimately, this application is going to be built out for doing compressible Navier-Stokes. So let's go ahead and set that out. Hence the fluids component in that name there. I'm going to change directories into that application. So if you don't have your application already on your Cloud shell, you can clone it down using git. Everything's already installed for you. And let's just take a quick look around at the source code just to remind you of what we got going on here. So if I did an ls, the way this project is set up is we have a source directory which has the .f90 and C++ files for doing basically it's our Fortran and our GPU accelerated code. We have a make file, self.make in the root level directory, and then we also have a Docker file already here. So this tutorial, I didn't really want to get into too many details that are specific to this application, but of course, in your case, if you don't already have a Docker file, just check out a few. There's a lot of resources online to learn how to write those from scratch if that's what you want to use. But generally, that Docker file, what it's supposed to do is specify a starting container image. In this case, it's this. It's what's specified here on this from line, and then everything else below are instructions on how to build your application and perhaps some of your application's dependencies. So in my case, we have a few dependencies on some tools like FEQ parse, JSON Fortran, Flap, and then of course we build our application down below. Let me make sure that's actually uncommented here. So I was doing some work on it earlier today. Like I said, this is all a work in progress. Things can break at any given time, so I hope you're along for the ride with me here. So I'm at this state now where I have a make file, I have a Docker file. The next thing I really need to do is set up a cloudbuild.yaml to run through the build process. And what we'll do next here is we'll set up that cloudbuild.yaml. We'll do a manual build to make sure that's all just going to go through without error. Of course, we just want to make sure we can communicate to the Cloud Build service. And then the next thing we'll do is we'll talk about how to set up some of those build triggers so that when you push to a branch, those builds happen automatically, and then we'll go ahead and implement our tests. All right, so the first thing we're going to want to do to create that build file, typically it's called cloudbuild.yaml. Now you can call it whatever you want and place it in any directory in your repository. Keep it easy. Call it cloudbuild.yaml, leave it in the root level directory. Now the main section of the cloudbuild.yaml is a region called steps. So you'll open that region with the steps, the colon, and then down below it's just an array of these build steps. Now a build step has a whole lot of metadata you can specify, but the bare minimum that we need to fill in the ID, okay, the name, and the arguments. Okay, so let's talk about these one by one. The ID is just a human readable name for that particular build step. So the first thing I want to do is actually just build that Docker container. So let's just say build, and I'll use single quotes here, Docker container image. Okay. Now the name for this build step, the way Cloudbuild works, so it's a serverless environment that in the back end, what it's going to do for each one of these steps, it's actually going to load a Docker container. And inside that Docker container, it's actually going to run your build step. And this might seem kind of bizarre at first, specifically because we're going to call up a Docker container that has Docker installed to run Docker build. But that's kind of the way you got to think about it. Highly recommend, and I'll just put this plug out there now, just check out cloud.google.com/cloudbuild. The documentation there is pretty superb. They've got lots of good guides to help you get your head wrapped around this stuff. But anyways, that name is going to be a container image to start from. So this could be any container that might be available on Docker Hub or that you have available on your own repository. Google also provides containers through the container registry. So that's gcr.io/cloudbuilders. These are all publicly available for anyone using Google Cloud. And underneath that particular repository, whoops, looks like I lost my connection here. Try to get that reset. Uh-oh. Okay, I think we just got cut off there for a second. Sorry about that delay here. Let's go ahead and get that Cloud Shell back up. Sorry about that. Okay, let's go ahead and reset my project there. I just got booted offline here. Sorry, guys. Okay, let's open up that cloudbuild.yaml. Recover. Okay, now that we're back in business. So there's a number of builders that are available through the Google Container Registry. They include Docker. If you're working with the NPM package manager, that's also there. Bazel, Git, Gcloud SDK, there's a ton of them. For our first step, since we're building a Docker container image, you can use Docker. Now, if there's not a cloud builder available, like if you want to use Singularity, for example, there is an open source repository that has a ton of community contributed Google Docker containers for working with Google Cloud Build, including Singularity and a number of others. So the next thing we need to do here is specify the arguments we want to pass into that container. Now, for the Docker container, the default entry point is the Docker command. And so all we need to do is specify the commands we want to send to Docker. So here we'll say Docker build is the first argument. Of course, the next argument for Docker build is the path that we want to use. Now, you can always assume that the path is going to be from wherever you submit the build from. And in this case, it's the root level of my repository. So if I specify dot, meaning the current directory, it's going to be working from the root level of the repository. So we're all good there. The next thing is we want to tag the image that we create, and we'll call it gcr.io, because with your GCP project, you actually have your own container registry. You can use a predefined environment variable in Cloudbuild for your Google Cloud project, so that the container image will post in your project's container registry. I'm going to call my application self, and then we'll give it the latest tag. Now you can give it whatever you want, of course. And then we can go ahead and close out that argument. And I'm just going to move that back up there. A little bit neater. I guess that's subjective. Okay. Now that's the main section that basically provides that single instruction how to build the application. Okay. Now down below we have images is the next one. So if you do create a Docker image, you can post that image to your container registry. So again, I'm just going to put the name of the image that was created, and this will automatically get posted to your project's registry. So that's really it. So we have the step for actually creating our application, and we have the step for publishing the application. So now what if we actually wanted to do those run tests? So let's back out of here real fast. Let's take a look at this Docker file. If I go down, I really want you to focus down here. Let's turn on that line numbering. After I'm installing all my application's dependencies, really line 31 and 32, it's running make install with my self.make, my make file. Okay? So if I look at self.make, right, it specifies the Fortran compilers, the HIP compiler that I should be using, my linker flags, includes flags, and of course all the instructions for creating self, the application. Now I've included with this application the way I do my testing right now is just really using a shell script that runs through a series of scenarios to exercise each one of the routines inside of self. So I'm doing unit testing. Just to give you an idea what that looks like, the self binary is set up thanks to Flap using a whole bunch of command line arguments I can pass to it. So for each routine I call, so in this case we're focusing in right now on, I guess I should back up here. Self basically does calculus operations using spectral element method, so we can calculate or estimate divergence, gradient, curl of vectors, tensors, and scalars. So the idea is if I give it a function to approximate, if I give it the nodal values of that function, I can have self routines spit back estimates of the derivatives. And the idea being here for like a divergence, basically what I'm doing here is passing in a vector field here. It's all one, so one in the x, y, and z directions. And of course the divergence of a constant vector should be 0. I've gone through a lot of work here to work out what the upper bounds of the errors should be when we do that estimation. So I can set a tolerance, basically say, okay, here's the exact answer. The exact answer should be 0. I can compute the estimated answer with my subroutine and basically say, hey, if the error that I find is larger than the tolerance I'm specifying, then of course I'm going to think that routine is failing, and I would mark it as a fail. If the tolerance is equal to or less than that, I would mark it as pass. And then I have a few other arguments that control like the amount of work I want to do in estimating that. So if you're familiar with spectral elements, this would be the polynomial degree and the number of elements here. Of course, the more work you do, the better the answer should be. And then of course I have flags for turning on and off GPU acceleration, and then some other specific parameters for each of these subroutines. But the idea being, I mean, this is a fairly large file. It's 778 lines. I've still got a few more to add into here, but it goes through and it basically runs these routines that do derivatives and interpolation for scalars, vectors, and tensors in 1D, 2D, and 3D on CPUs and on GPUs. So it is a bespoke script right now, but this is currently the test that I run every time the code I want to commit the code. I'll compile it and then I'll run this bash script to see if all my routines are still working. Now, so what we want to do is make sure that after I build my Docker container, I want to call Docker back up to run a command inside that container. What I want it to do is run that ci.sh inside the container. So we'll go back into that cloudbuild.yaml. I'm going to add another step down below. Okay, we have the ID again. In this case, we're going to run the CI tests. Okay, and we have name. Again, we're going to use that Docker Cloud Builder. Okay, and then we'll have args. In this case, we're not going to be building, we're going to be running. And what are we going to run? Well, we're going to run that image that we just created. So we'll run gcr.io/project ID. Okay, self latest. And now we can tell it the commands we want to run inside that container. So at this point, we have a container that has the application installed. ci.sh is installed in there. So we need to do bin/bash, and then we need to run the ci.sh. So let me look back real quick at that make file to see where I install it. So I have a prefix here, apps self, and ci.sh down here on line 19 is copied into apps self, the prefix /bin. So that's what I need to run. I have apps self bin ci.sh. And so what should happen here is the nice thing about Cloud Build is if any one of these steps fail, the whole build will fail. And it will, and if the Docker container image build fails, it won't try to run the CI test. It'll just stop at that first step. Now, if you do have more complex build pipelines, there are a lot of cool things you can do to bypass certain steps if they fail. Maybe they're non-critical failures, so you could do stuff like that as well. Okay, so that's really it on the cloudbuild.yaml. I want to show you how to set manually trigger that build, and then I want to show you how to set up a build trigger based off of a branch, and we'll just demonstrate that actually kicks off the build. Keep in mind, my CI test might actually not be passing at the moment. That's again because this code right now is in a work in progress state. So right now we got gcloud builds submit is the command you would run to launch that build manually, and the argument that goes in there is the path that you want to execute the build within. What this means is this current path or whatever path you put there is going to be recursively bundled together and copied up to Google Cloud Storage and then set up in an isolated environment where Google Cloud Build will run. I like to pass the async flag so that I can get my command prompt back. And of course, if you if you spell it wrong, it's not going to run. So let's correct that. Okay. So it packaged it all up. It sent it up to the Cloudbuild service. Let's go back to the console here real quick so you can see where you might look at the history of your application's build. So if you click on that navigation menu, of course, you can use the search bar there to search for Cloudbuild. If you scroll down, we're going to go down to Tools, and you got Cloudbuild. Okay, so you can see the history here. Of course, I've got a mix of passes and fails, but that's really because I test every single commit, and I do want to just keep progress moving along here. But once you get inside each one of these builds, you're able to see the build logs of what's happening. So if you do have a failure, you're able to see exactly what went wrong during the build of your application. If you want to recover specific execution details, maybe you have specific flags that you want to change from time to time. We'll be getting into a lot of those things next week, specifically when we get to the GPU builds. But all this information is there for you to find on the Cloudbuild dashboard. And of course, there are a lot of commands that are available through the Gcloud SDK that allow you to programmatically pull down that information. While that's building, let's go ahead and set up some triggers, and then we'll make a push to a branch just to show you that it's working, and then we'll be done for today. So let's go over to triggers. Once you're in that Cloudbuild menu, and you'll hit Create Triggers. Now, if you haven't connected any repositories, it's a good idea to go ahead and hit Manage Repositories so you can connect your GitHub, your Bitbucket, or your Google source repositories Git repo. So we'll go ahead and hit Create Trigger. Up here, I'm just going to call this Demo Cloudbuild. Okay, it's a good idea to give this a description. And there are 3 different events you can have to trigger a build of your application. It can be a push to a specific branch, push of a new tag, or if you're on GitHub, there's actually a cool connection there. Whenever a pull request is open, you can have builds happen then, and it can actually publish information back to that pull request, which is really nice for giving visibility to other developers who might not already be in your Google Cloud projects. Now the repository, again, if you haven't connected your repository yet, when you click that drop-down menu, it'll give you the option to connect to a new repository. Now I've already done mine here. I've got self-connected via a GitHub app. And the branch I want to use, let's just call the branch instead of main. You'll obviously, if you haven't noticed, you'll need to use a regex statement here to filter out which branches you want to build. Let's call this, let's say dev, and we'll just make a new branch here and we'll push that up. Okay. Now the build configuration, of course, if you've just made a cloudbuild.yaml in your root directory, auto-detected will work just fine. Now, if you did put it somewhere else, make sure you select the cloudbuild configuration and you can specify the path to your cloudbuild.yaml. That's really helpful if you have a set of triggers, maybe one for dev, one for prod, and maybe some for your feature branches or your bug fix or hotfix branches. Whatever it is you're doing, you can set up a whole array of these triggers to accommodate your needs. Okay, so I know that if I push to a branch called dev, this should actually kick off a build. So let's go ahead and do that. Let's say git branch or git checkout -b dev. So make a new branch. Let's add our Docker file and our self.make and the cloudbuild.yaml. Okay, let's commit that. Okay, demo commit. I'm not going to worry about that now. And let's push that up. Whoops, of course, it's a new branch. So let's say git push -u origin dev. Okay, so now it pushed that repository that made that commit. I made a commit and I pushed it back to my repository. So if I go back here to the history, we'll see now we've got a build that already happened because of that demo cloud build trigger. So I hope you guys found this useful. Of course, if you have any questions, feel free to reach out to me over the chat. Of course, you can reach me at support@fluidnumerics.com. I'd love to talk about what it is you guys are doing, especially with these Fortran applications. Next week, we'll be looking at adding to this build step some connections to Google Compute Engine so that you can build applications and test them on GPU accelerated hardware. One of the issues with Cloudbuild is out of the box, the environments that they run in, they only have CPUs, and you're limited to, I believe, 64 CPUs. So even if you want to do multi-VM or MPI jobs at scale as part of your testing, you're going to need to connect to Google Compute Engine. So we'll be starting to talk about that next week. Again, thank you for joining, and I hope to see you guys next week.